Hi, welcome to our last few Level 3 integration videos. In these last couple of videos, we're going to turn our attention to differential equations. Everything we've done so far in mathematics is trying to solve equations that perhaps give one, two, or more solutions. Here's an example of an equation that has one solution. This quadratic's got two. This trig function's got many, in fact, infinite solutions. Now we turn our attention to differential equations. Differential equations are equations that express change. The solution to a differential equation, not going to be a number, but a function for the answer. Here's an example. dy over dx is equal to 4x. This is a differential equation. And when we solve it, by integrating on both sides, we get a solution, but it's not going to be a number. It's going to be a function or a rule. Okay, let's quickly look at the four types of differential equations you will come across in the standard. If we say the rate of change is constant, the differential equation dy over dx is equal to some constant k. If we say the rate of change is proportional to x, the differential equation dy over dx is some constant k times the function x. If we say the rate of change is inversely proportional to x, or dy over dx is equal to some constant k times 1 over x. 1 over x is the inverse of x. And finally, if we say the rate of change of an amount is proportional to the amount itself, we're going to say the rate of change dy dx is equal to some constant k times the original y function. We're going to explain these a lot more as we do the next couple of videos. But for now, let's get you used to reading stories and writing them into equations. So here's example 1. The height of a bamboo plant is increasing by 4 centimeters per day. Express this as a differential equation. Well, here's the four types. And even though we didn't use the word constant, we're talking about a constant increase of 4 centimeters per day. So dy over dx is k. But we're just going to change it into dh over dt is equal to 4, because h represents the height of the bamboo, t represents the time per day, and we have 4 centimeters per day is our k. Right, example 2. Water's flowing out of a bathtub at a rate of 25 litres per minute. Express this as a differential equation. So again, we didn't use the word constant, but we're constantly losing 25 litres per minute. So it's going to be dy over dx equal to some constant k. But k is going to be a negative number because we are losing water out of the bathtub. It's decreasing. And we're going to change dy dx into dc over dt. C would represent the capacity or the volume of the water, and t would represent the time in minutes. All right, what about this one? Example 3, a runner is running at a speed that's proportional to the function 0.4x squared minus 0.5x, where x is the distance left to run. Right, this is a differential equation. Well, we're using the word proportional to a function of x, so we're using this differential equation. So we're going to say dy over dx is equal to k times x. And we're going to change that to dv over dt. dv is speed and dt is time. And we've got some constant k times the function x, which is 0.4x squared minus 0.5x. Right, finally, example 4. The population of New Zealand is increasing in such a way that the rate of increase is proportional to the number of people in the country at any time t. So how do we express this as a differential equation? Well, we're using the third one that we're looking at in the video here. dy over dx is equal to ky. So we're going to write this as dp over dt. dp means change in population over dt, which is change in time. And we're going to put that equal to some constant k times p, which is the size of the population at any time. Right, we didn't do the fourth example, but we will look at these later in some more videos. Great, thanks for watching.